Hello, chemistry students. This is Professor McMahon here with Chapter 7. In this series, we'll have at least 4 lectures for Chapter 7 because it's covering the topics of chemical reactions and quantities. We'll see that the earlier chapters where we learned nomenclature, so in Chapter 6, how to write out chemical formulas, is critical for our understanding for this chapter, but really, when you think of chemistry, this chapter is the nuts and bolts of chemistry. Reactions that we observe and determining how much of something we can produce. If you think of the industry, pharmaceutical industry, any type of industrial industry, how much product can I produce? That's what this chapter is going to do for us. It's going to show us how to calculate that. But before we can calculate how much is produced, we have to be able to identify reactions, write them out, and balance them. And that's what this first lecture is going to get us into. So pretty much everything around is powered by reactions, whether it's your car, laundry, processes in your body. It's all chemical reactions. It's all movement of electrons, because in reactions, that's what you're doing. You're moving atoms around to stabilize them, to fill their shells so that they're stable. And the way you do that is by either losing and gaining electrons or sharing electrons, breaking bonds, forming new ones. So chemical reactions, right, produce changes and rearrange the atoms. So we burn octane in an engine with oxygen to support the combustion to produce CO2 and water. But really, what we also have to take into account is we're not really burning fuel to produce CO2 and water. We're burning the fuel and we're putting this chemical reaction through because it's also accompanied with energy. So that's why we learned matter and energy in Chapter 3. Really, this chemical reaction is a driving force for something we need to have done. Just like you consume food so that you have energy so you can do your daily tasks. So how do we know if there's been a chemical reaction, which essentially is a chemical change? There's a color change. If there's some formation of a precipitate. Precipitate's just a fancy way of saying solid, and shorthand version, I'll be writing PPT because to write that over and over with my pen, it's just not going to be neat. Formation of a gas. So I don't mean I have water, for example, and I put energy into the system and boil it. That's not really a chemical change. That's a physical change. That's what we just learned, separating, using the energy to separate the molecules so I boil. I'm talking the formation of a gas is if I take 2 liquids at room temperature and I combine them, and then there's bubbling, okay? You can think of also, you're probably too young, but Alka-Seltzer commercials where you would drop an Alka-Seltzer in water and it would start fizzing. That is an example of formation of gas. You're not boiling anything there. Oh, whoops, I wouldn't let emission of light. So when you burn, let's say magnesium, for example, bright light is emitted. That is evidence of a chemical reaction. Fireworks. Emission of heat. So sometimes you don't see anything. There's not a color change. There's no formation of gas. There's no light, but heat will be a release. And a lot of times, or absorbed, you can touch like a test tube. If you take 2 clear solutions, like in a neutralization reaction, you have an acid and a base. They're clear solutions. You combine them and they produce water. The water's, it's all dissolved in water, so you don't see anything. But if you touch the test tube or the beaker, it'll release heat. That's evidence of a chemical reaction. So how do we write chemical reactions or equations? Well, we use symbols and formulas. So in this equation, we have methane, CH4, and oxygen, and their reactants. So typically your reactants are on the left side. They're your starting material. I'm having trouble with my pen again. Your products are what you produce. They follow the arrow. It's called yield, and your products are on the right side. We usually in chemical reactions have to, okay, specify the physical state. So a subscript little g is gas for gas, L liquid, S solid, and AQ is aqueous, which means it's basically dissolved in water. That's what aqueous means. It's a solution. I took a salt, I threw it in water, and it's dissociated into its ions, and now the ions are in the water. You can think of it when you add salt, table salt to water, okay? And aqueous, aqua, agua, that's where it's derived from, in water. So there's an example where you might look at the physical states in a subscript form. So let's look at chemical reaction here. The equation can be read above as follows. We have aqueous barium acetate, so it's aqueous, and this is barium and this is acetate. It's dissolved in water. How do I know that? Aqueous. So I took this salt, barium acetate, I dissolved in water. I added to another solution of sodium carbonate. How do I know it's a solution? Aqueous. So I took sodium carbonate, dissolved in water. I take the two solutions. They're going to produce a sodium acetate solution and a solid barium carbonate. And so solid barium carbonate, and I show that. This is actually an example of a precipitation reaction. Why precipitation? Because I said earlier, precipitation is just a fancy word for saying solid. I made a solid. That would be evidence of a chemical reaction. So if you're in a lab and you take two solutions and a solid's formed, you're like, something happened. And this would be a way to express it by writing out the chemical reaction. So you have to know what your reactants are, and you have to know what the products are. So let's practice. Now, this is tricky because if your nomenclature is a little weak, you won't be able to remember this. So first, you have solutions, that means aqueous, of sodium carbonate. So don't get careless here. You have to remember, sodium is a metal, carbonate is a polyatomic ion. This is an ionic compound, which means I need to think of charges. So sodium is a +1, carbonate's a CO3 2-, okay? And that solution of sodium carbonate is combined with magnesium chloride. Magnesium's a metal, chlorine's a nonmetal. Again, binary ionic, so I have to think of charges. Mg2+, Cl-, okay? So the first thing is I have those as my, whoops, I have those as my reactants. So Na+, CO3 2-, I crisscross and I get the sodium carbonate, and it's aqueous. Plus, remember the magnesium chloride. To get the correct formula and the right ratio, I have to crisscross. So I get plus the NgCl2 aqueous. React to form a solution of sodium chloride. So that's why that's AQ. Sodium, again, is Na+, it's ionic, and chloride, it's not. So sodium's a metal, chloride's a nonmetal. +1, so it's a 1-to-1 ratio. So there's no subscripts needed to make this a neutral formula. And solid, that's why this is a reaction. I produce a solid, magnesium carbonate. Magnesium is a, whoops, don't know what happened there. Magnesium is a metal. Carbonate is a polyatomic ion, and I know it's 3 because it's not on the 4 if you're watching my videos. So now I have to do the crisscross, but because the magnitude of the charges are the same, I want to simplify the formula so it's 1-to-1. Oh, and here's a careless mistake. This should be a solid, magnesium carbonate. So see, your teachers can make careless mistakes too when they're tired. But we caught it, we're all good, okay? Now, we'll see that this isn't balanced, okay? But that That'll be the next exercise. Let's focus on just writing it out. So again, a solution of aluminum bromide. So aluminum's a metal, bromide's a non-metal, so I have to think of charges. I need a crisscross. And it's a solution. Reacts with chlorine gas. Okay, so now chlorine is an element. And they're telling me it's a gas because in nature, you find that element of chlorine as a gas. Now, why did I write 2? Because chlorine's one of the 7 diatomics. So if I say chlorine, it's like saying oxygen. It's a diatomic. So if chlorine's by itself, okay, it's not in a compound, it's a diatomic in elemental form. To produce a solution of aluminum chloride, so aluminum's +3, Cl-, I'm going to crisscross. It's a solution. And liquid bromine. Bromine is another diatomic, so it's as an element, and it's the one of 2 liquids of all the elements. Bromine and mercury are the only 2 liquids that are in elemental form. So this is an element, this is an element. Why? One type of atom. This is a compound, this is a compound. Why? More than one type of atom. This is binary ionic, binary ionic. Why? Metal, non-metal. That's how we got the formula. So we write that out. And we will need to balance this. So the reason why I did it twice was because you might not, my writing is not the greatest, so I made sure to also show you it in clean form. But I like writing it to show you how my process of thinking is, and also you keep up with it better. So the one thing that I did not do, and we have to do this when we're writing out chemical reactions, is I need to have a balanced chemical equation because you need to have the same number of atoms on both sides. We can't create or destroy matter. We can just move it around, okay? We can't do it, okay? So the equations must be balanced to comply with the law of conservation of mass. That's just how it is. So when we balance, you can't change formulas to do it because the formulas is the correct ratio for that compound. So you can't change the formula. So we can manipulate subscripts, but what we can do is use coefficients to help balance. Coefficients are in front of the formulas. So here are these are my rules. This is an actual link. If you want to go and watch a video, you can click it. You don't have to. Some people like the shorter videos. Again, for this sequence of videos, I decided to treat it as if this is a lecture for an hour and a half or an intro college course. If you like shorter videos on just balancing, you could click this link right here and watch it. But the basic rules for balancing equations are: first, you want to balance the metals. Now, that's because they're cations and positively charged. I group the polyatomic ammonium with them because it has a positive charge. The second thing I want to balance is nonmetals. If I have a polyatomic ion, an anion on both sides, I don't want to break it up. So if I saw sulfate on both sides of the equation, I don't want to separate it into sulfur and oxygen. I just leave the whole group. It's easier to balance. Third, I'm going to save hydrogens and oxygens for the very last of the nonmetals. Okay, so first metals, then nonmetals, but I save hydrogen and oxygen last because they're the most common, and I want to save those. If I have a bunch of hydrogens and oxygens and both of them, then whatever is a diatomic on one of the sides, I save for the very, very last. So like if I have an O2, then hydrogen would go first, and then I would do oxygens, because that diatomic, that element means I have oxygen by itself. It'll make it easier for me to balance. And then obviously you gotta, sometimes you change coefficients and you gotta work your way back and check. Kind of like in, coefficients with polynomial functions. So let's write a balance equation for what we had before, right? Actually, this is an example. When aluminum metal reacts with air, it produces a white powdery compound called aluminum oxide. So whenever it says it reacts with air, it's basically reacting with oxygen. The major component in air is actually nitrogen, about 79%, but it's highly unreactive. Yeah, there's 19% oxygen. Oxygen is extremely reactive. That's why you hear the term oxidized. So whenever you hear with air, it's oxygen, okay? So it's an aluminum metal, so it's solid at room temperature. Oxygen is a gas, it's a nonmetal, and a powdery compound. Powder is a solid, so the aluminum oxide is a solid. Now, in elemental form, aluminum is just Al, and I know it's an element because it's just aluminum. In elemental form, oxygen is one of the diatomics, so it's O2, but this is a binary ionic compound. So aluminum oxide means there's aluminum and oxygen. And when I combine a metal with a non-metal, it's ionic. I have to think of charges. So 3 plus, this is 2 minus. So I have to crisscross to get the correct ratio. And that's where I get aluminum oxide is Al2O3. Okay, now I need to balance it. So for my rules, there might be a little bit of back and forth. I got 1 aluminum, 2, I might put a 2 here. I have 2 oxygen and I have 3. Well, what's the common thing that they both go into? They both go into 6. So 3 times 2, 2 times 3. Now the oxygens are balanced because I have 6 on each side, but remember that last step, I need to go back and check my work. I put 2 aluminum and each aluminum oxide has 2. So 2 times 2 is 4. So I'd actually have to go back and make that 4. So there's my balanced equation. Okay. What if I have something like this where I have OH hydroxide and H plus? I always tell students, and the reason why I know this is H plus is because sulfate's a 2 minus. And that is sulfuric acid, one of the oxy acids we discussed. It's diprotic because there's a 2 negative on the sulfate. We know sulfate has 4 because it's on the 4. And that's why there's 2 of those. But whenever you have an acid, how do I know this is an acid? Because the hydrogen's in front, and a base. How do I know this is a base? Hydroxide is a base. Whenever I have that, and I'm trying to balance, trust me, this is a neutralization reaction where I'm having an H plus and an OH minus coming together to produce a neutral water molecule. So I always tell students, treat the H pluses and the OH separately when you're balancing neutralization reactions that have water, okay? And you can even write it as HOH to help you balance, but use that OH to let you know, hey, I'm gonna keep this separate, all right? You'll see later when we're doing a little more balancing. But for this, right, sodium bicarbonate, we already kind of did this in sample exercise 2. Solution, with a solution of magnesium chloride produces sodium chloride solution and solid magnesium carbonate, except for I messed up right here, so I apologize. So I need to balance it. So first, metals. There's 1 or 2 sodium right here because of that subscript. Why 2 sodium? Because if you remember, sodium's plus 2, carbonate was 2 minus. I need 2. But I don't want to change the coefficient of the subscript here and make that an Na2Cl because this is a 1-to-1 ratio. So what do? I put a coefficient of 2. So now I have 2 sodiums. I did metals first. Magnesium's a metal. 1 magnesium, 1 magnesium. Okay. Then I go to non-metals. I have 2 chlorine here. And what do I have? 2 chlorine here. So my chlorines are balanced. And then I notice that there's a carbonate on this side and one on this side. There's no need to separate the carbons and oxygen, keep it together. I have 1 carbonate here, 1 carbonate here, I'm balanced. So those are the rules. Metals first, I went to sodium, then magnesium, then nonmetals, chlorine, and then I group the polyatomic anion, which is negatively charged, and balance that. Let's try it in the other one. So first, we would go metals. All right, 1 aluminum, 1 aluminum. Then I would go to nonmetals. 3 bromine on this side, 2. What's the common denominator? What do they both go into? 6. So 2 times 3 is 6. 3 times 2 is 6. Uh-oh, I switched the aluminum. What did I switch it to? A 2. So now I have to put a 2 here. Well, 2 times 3 chlorines is 6 chlorines. So 2 times what? 3 chlorines. Now I'm balanced. Takes a little bit of practice, right? But you'll get good at it, trust me. So now that we know how to balance, and I'll continue balancing. We're by no means done balancing. This whole lecture will have balancing in it. But we also want to be able to classify reactions and be like, okay, this is the type of reaction this is. Because down the line, we'll have to be able to predict products. You'll just be given reactants, and you'll have to predict products. So a way to identify the type of reaction that takes place is looking at the groups. Okay, earlier I said, whenever you see a neutralization reaction, that's an acid and a base producing water, you should balance the H pluses and OH minuses. Well, what did I do? I looked at the group of atoms to help me classify it, to make it easy for me to identify the reaction. Well, that's what we got to do. So there's 5 basic classes. Again, these are active links. If you want, you can click on these and go to a shorter video. I'm treating this as a long lecture. But the different types of reactions are combustion, synthesis, which I like calling the synthesis personally combinations, because combinations are where you take 2 or 3 or 4 things and combine them into one. Okay, so that's what a combination is. Decomposition, you take one thing and it breaks down and decomposes to multiple. These are basically the opposites of each other. Double displacement, I put on the side here aqueous reactions. Why? Books tend to talk about many reactions separately, and it gets kind of overwhelming. So a lot of times they'll classify things as precipitation reactions, gas evolution reactions, aqueous reactions, redox or oxidation reduction reactions. What I'm telling you is, if you know the 5 basic types, you'll see that the 5 basic types are more specific than just saying aqueous reactions. Why? Because, and double displacement, there's 2 types, neutralization and precipitation. I'll go over both. Okay, so precipitation is a type of double displacement. That's actually a little more specific than just double displacement, but it's okay. But the 5th is single displacement, and what I want to show people is, if you say it's an aqueous reaction, that's not enough, because there's multiple reactions that are dissolved in water. That's what aqueous means, in water. So that's not specific enough. So for our class, when you have to identify something, you're looking at these 5 basic types. Now, not all reactions fall perfectly in these 5 basic types, especially when you get to organic chemistry. But for this general chem course intro level, these are the 5 basic types that I want you to be able to identify. So they kind of show you, what it is. So here's an example of the combination or synthesis. You have 2 reactants forming 1 product, okay? So in this example, they take a metal and a non-metal, and what are they going to combine to produce? an ionic compound. Now that's the easiest of all the combinations. Why? Because if I see the metal calcium, I could say, oh, that has a 2+ charge, and the non-metal chlorine has a -1, right? So then I could crisscross and figure out the actual ionic compound that they come together to produce, because that's what a combination is. A metal and a non-metal coming together to produce an ionic compound. Decomposition. I have something that breaks down to multiple parts. So here I have an ionic compound. So this is iron 3 sulfide, and it breaks down into iron in an elemental form and sulfur. Really, that should be S8, but this is an intro class, so I'll chill out. But yeah, they made it a little bit easy. It's actually a molecular element, but I'm not going to get into that. That's okay. Single replacement. That's where I have an element and a compound, and one element kicks out the other element and forms a new compound and a new element. So when I look, copper is an element, okay? It's a metal. Silver nitrate is a compound. It's an ionic compound. The copper comes in here, kicks out the silver to form a new compound or new element, right? So a new metal, this element, copper, kicks out the silver to produce a new element, silver, and forms a new compound. So here I have silver nitrate, here I have copper 2 nitrate. Okay, that's single displacement. You could think of it as, here's a single person, here's a couple, this guy butts in and kicks out this guy, and now there's a new couple. I hate to post something that's kind of cheesy, but yeah. The only reason why I do that is because double replacement is a compound and a compound, and we have a switching of partners, and now I have a new compound and no new compound. I basically call it the do-si-do. So you basically have a switching of partners. And now the barium chloride becomes barium sulfate. The potassium sulfate becomes potassium chloride because sulfate and chloride switch with one another and form 2 new compounds. The easiest of reactions, and I actually, when I said the 5 basic types, I list combustion first. Okay? Combustion, in my opinion, is the easiest. Why? 3 of the 4 things in the reaction are always the same. To support combustion, you need oxygen. So oxygen's always a reactant. CO2 and water are always products. What changes is the fuel you're burning. So, I use the example of octane, right? It could be methane, what's found in Bunsen burners. It could be, they didn't do this for your course, but in reality, for combustions of organics, there could be an oxygen here too. So like glucose, right? Glucose is an internal combustion. We eat food to burn that fuel source. Why? To produce energy in the form of ATP. Okay. If I was to rank as far as difficulty, combustion's the easiest because only one of the things changes, the fuel. Then I would say combination because it's typically like a metal, non-metal, ionic. Third would be decomp. 4th would be double, and then single, and that's how I lecture. Okay, I saved the double and the single last because they're both considered aqueous reactions. Okay, but I know this is quick, you're gonna get mad, but let's classify these. And as we move forward, I'll be more specific. So if I look at this, okay, I have 1 compound, 2 compounds, and I produce 1. So where do I have 2 things coming together to make 1? Is that a decomposition, a combination, single displacement, double displacement, or I forgot to write combustion, my bad. It's a combination. I got 2 things coming together to make 1. Okay. Now, what do I have? I have a couple and a couple. Here I have a couple and a couple, but what's different? Why is there a reaction? What I notice is that sulfur and chloride switched partners. It's like a dance. They did the do-si-do. They switched partners. So the two compounds produced two new compounds. That's a double displacement. Why? Both compounds changed. So it's a double do-si-do. Do-si-do, it's a double displacement because both couples changed. And there's two types, we'll talk about it. One's neutralization, where I make water. The other is a precipitation, where I make a solid. Now, what about this? This is nickel 2 sulfite. Okay. It's only one. What does it do? It produces two things. Where does one break down to two? Decomposition. Okay. Now, I wouldn't expect you to memorize what the products are in this decomposition, although this is an example of a gas evolution reaction. Typically, for this to occur, you'd have to have heat. Whenever you see a triangle over an arrow, it typically means you're heating it up. There's a heat. Now, this one, I have an element and a compound. I form a new element and a new compound. Or wait, sorry, let me redo that. Here's an element, here's a compound. Here's a new compound. Why is this a compound? Because there's more than two types of atoms in a new element. So what happened? Chlorine, well, really calcium kicked the lead out. Calcium said, hey, I'm going to dance with chlorine. Get out of here. Boom. So what is that? It's not do-si-do. It's, when you think of an element, it's by itself, it's single displacement. And then last but not least, this is propane found in your, propane tanks when you barbecue. And what do I notice? Oh, one of the reactants is oxygen, supports combustion. I produce CO2 and water. This is combustion. Now I know this is, a little tricky, but we're going to try it. All right. So for this first one, what do we notice? I have an element and I have a compound. The element's nickel, which is a metal. Here I have a new element and a new compound. So what happened? So basically, the nickel kicked out the hydrogen, and now it combined with the chlorine. So this is I didn't write, sorry. Must have forgot this one. This is a single displacement, right there. What about this? Hydrogen peroxide. I have one thing as a reactant. It produces two. Water and oxygen. This is a decomposition. What do I have here? An element, metal, another element, non-metal. They come together. So two things come together and produce an ionic compound. So this must be a combination or synthesis, depending on your book. What do I have here? I have a fuel source, oxygen, which supports combustion, produce CO2 and water. This is combustion, not combination. Spelling matters. If you try to mix these two, you're going to get it marked wrong. There's not a hybrid. Although no, I'm not going to go there. So what do I have here? I have a compound and a compound. What do I produce? A new compound and a new compound. So these couples are swingers. I switched partners. So this is double displacement. So let's really kind of start breaking everything down. Okay, so combustion reactions is a type of oxidation reduction. So you can't just say redox. It's too vague. 4 of the basic 5 are redox. So I want you to be able to identify it as combustion. So how do you do that? Well, in these reactions, like I said, you're always going to have oxygen as one of the reactants, and you're going to produce carbon dioxide and water. All of the carbon goes in from the, all of the carbon of the fuel goes into the carbon dioxide. All of the hydrogen of the fuel goes into water. And sometimes the fuel can have oxygen as well. So this is like a generic type, right? You have some fuel, you can change these variables, it doesn't matter, but you're always going to have O2, CO2, and water. And the reason why I wrote gas, liquid, at room temperature, water is a liquid, but combustion reactions, we don't burn things because we want to produce CO2 emissions. We burn things because we want the energy, right? So they're typically, they release a lot of energy and heat, which causes the water to vaporize. So it's more accurate to write water as a gas. I typically accept if you put liquid because it can, in theory, recondense, but typically it'll stay in the vapor form. So here's methane, right? Methane is tetrahedral in arrangement. You have a carbon with 4 hydrogens, CH4, and it's a gas. I take 2 oxygen diatomics. So this is an element, even though there's 2. Why? Only one type of atom. Combine these through burning them to produce CO2. So 1 carbon, 2 oxygen, and then 2 water. And we see that this follows the law of conservation. So what we want to practice is balancing and identifying. So is this a combustion reaction? Yes, there's a fuel source, pentane. There's oxygen, CO2, and water. So first I want to balance metals. No metals. Where do I go? Non-metals. I save hydrogen and oxygen for last. So the other non-metal is carbon. There's 5 here, so I'm going to put a 5. Okay, so carbons are happy. Now I have both hydrogen and oxygen. Remember I said, if I have both, who do I save for the very last? The diatomic. Oxygen's a diatomic. So I'm going to go to hydrogen first. So hydrogen, there's 12. I have 2, so I put a 6. Why did I do that? Now I can look at all the oxygens in my products and just focus on the coefficient in front of the diatomic. So 5 times 2 oxygen, okay, because that's CO2. Every carbon dioxide has 2 oxygen, and I'm saying there's 5 of these. That's 10 oxygens, plus every H2O has 1 oxygen. I'm saying there's 6. 6 is a total of 16 oxygen. So 2 times what number is 16? 8. And I'm balanced. Good old cellular respiration, right? Glycolysis, right? And the Krebs cycle and the electron transport chain, basically cellular respiration. And you could have learned it as either 36 or 32 ATP, depending on the book and the time period. That's another class. But what I'm showing is here I have a fuel source, glucose, okay? It's an internal combustion. So what does that mean? Oxygen, cellular respiration. I'm inhaling the oxygen and air. What am I exhaling? CO2 and water vapor. Exhalation. Now I need to balance it. Carbon first, 6. Then hydrogen, 12. 2 times 1 number is 12, 6. Then this is tricky, right? Because now I want to go to the oxygens, okay? I'm going to save this reactant side last because that's where the diatomic is. And I'm going to first go to the products. 6 times 2 is 12. 6 times 1 is 6. So I need to cancel out 18. What a lot of people do is they get hyped up and they go, oh, 18, 2 times 9 is 18. They are wrong because what they are forgetting is in this fuel source, there's O6 in the glucose. So yes, on this side, there's 18, but we got to go 18 minus the 6 in glucose leaves 12. So now I need 12 more. How do I do that? 2 times what number is 12? 6. So see, the nice thing is when you know chemistry, you don't have to memorize this equation. You could just say, you know, cellular respiration is a 6-carbon carbohydrate, and it's an internal combustion. You'd be like, oh, combustion, O2, CO2, and H2O are products. What did he say? A 6-carbon carbohydrate. Well, what do I mean carbohydrate? Carbon hydrated with water, 6 carbons. Because glucose is 6-membered ring. And then boom, 6 times 6, when I distribute that, I get this. For now, we don't have to worry about the formulas for carbohydrates, but you do have to be able to balance this and identify this cellular respiration, just like the combustion of methane and pentane as a combustion reaction. Let's go to the synthesis or combinations. So typically, the one that I expect you to know is if I give you a metal and a non-metal, you're going to produce a salt. Salts at room temperature are solids, right? Think of table salt. Metals are solids. Non-metals can be solid, liquid, gas, depending on the non-metal. So here's an example. Magnesium, it's a solid. Oxygen, it's a diatomic, and it's a gas. What am I producing? Well, if I take magnesium, which is a metal, and oxygen, a non-metal, I'm making magnesium oxide, okay? But people get confused because they try to write this out, MgO2. That is wrong. Why? With ionic compounds, you have to be like, oh, I got to think about the charges. I look at the periodic table, magnesium is group 2, so it's a +2. Oxygen's group 6, it's a -2. So when I see that these are the same magnitude, I would crisscross, it'd be Mg2O2, but we want to simplify. So it's just MgO. And now to balance it, I first do metals, 1 magnesium, 1. Then I do non-metals, 2 oxygen. There's only 1 on this side, so I put a 2. Check my answer, 2. I'm done. Is there another example? Well, yeah, doesn't always have to be a metal and a non-metal. It could be a compound with another compound. We saw that as one of the examples in the sample exercises. The one that I want you to really be comfortable with is this, because we've already discussed binary ionic, right? Binary just meaning there's one type of metal, one type of non-metal. So you should be comfortable in identifying that and predicting the product. Here, you don't have to predict the product, but you should be able to say, hey, I got 2 things, they're combining, producing 1. This is a combination. So now I need to balance this, right? So how can I balance this? Well, I got 1 magnesium, 1. Now I don't really have hydroxide on both sides, so I could just say, all right, I need 2 oxygen. I got 1, 2, and I need 2 hydrogen, 2 hydrogen. I'm balanced. Okay. What about a decomp? So for decomp, what could you do? Well, for a decomposition, right, I'm going to take a substance and break it down to multiple. So here is water. I put enough energy in, I'm going to separate it into its oxygen elements and its hydrogen elements. So I'm breaking down a compound into elements. That's a general equation. This is a very common reaction. This is where I have a metal carbonate. How do I know it's carbonate? CO3. How do I know it's a metal carbonate? Calcium's a metal. And they produce metal oxides and CO2. Basically, your carbonate is breaking down to an oxygen and a CO2. That's how you can think of it. okay? And that O2 that O carries a 2 minus charge, okay? So if I want to balance this, one metal, one metal. Now I don't have carbonate on both sides, so I can't balance the carbonates. So I'm going to go carbon first and save the oxygen for last. One carbon, 3 oxygen, 1 plus 2 is 3. This is already balanced. Let's try a trickier one. This is another common decomposition. So metal carbonates, but in this case, it's metal chlorates. With both of these, I'd have to heat it up too. Basically heat it up and it decomposes it. Like here, to decompose the water, I need electrical energy. Do it with the battery. But basically, metal chlorate, this is chlorate. How do I know? It's not on the 4, just like the carbonate, not on the 4. It's a metal chlorate, and it breaks down to what? A chloride and oxygen. So now I want to balance. 1 potassium, because metals go first. The chlorate is not, this is not on both sides, so I have to separate the chlorine and the oxygen, okay? Because I want to save oxygen for last. So 1 chlorine, 1 chlorine. So far, so good. Uh-oh. 3 oxygen, 2. What do they both go into? 6. So I have to multiply the 2 by a 3 and the 3 by a 2. Uh-oh. I have to go back and check my work. There's 2 potassium, and that takes care of the 2 chloride, and I'm done. So that's a decomp. All righty. I actually think this is a good starting point. I didn't cover all the 5 basic types just yet in detail. I mean, I covered them very preliminary. I covered in detail more the combustion, the combination, the decomp. In my next lecture, I will finish my discussion of the double displacement and the single displacement and how they are aqueous reactions. And then I'll go into what I mean exactly by oxidation reduction reactions. So this is kind of the preliminary lecture for chemical reactions and their quantities, being able to balance equations, write them out, and identify them based on the groups of atoms. And next time, we'll finish with the last 2 basic types, double displacement and single displacement. Thanks so much for watching, and I appreciate your patience.